Hi, in today's video we will start with our unit number 7, that is nothing but supervised learning. Within supervised learning we have two different broad categorization, classification and regression. We will first proceed with classification modeling. We will first discuss classification modeling step and a very good classification algorithm, which is nothing but K nearest neighbor, KNN. We will see different examples which are solved using KNN problem, different challenges that is faced by KNN, application, strength and weaknesses of same. First, we will see what is supervised and unsupervised learning. So, supervised learning can be performed on training data which is labeled type. Labeled means for some set of training data we are given what is their target class, and that target class is trained over a given model, and using that training data an unknown data can be later on classified with one particular label. In contrast, unsupervised learning can be performed with the help of unlabeled data which is used for training, in which we have set of training data but target class is not given as an input. System has to group these unlabeled data into particular way so that it can decide the target class of unknown data. In between, there is something called as semi-supervised learning, in which some part of training data is labeled and some part of training data is unlabeled. This semi-supervised learning and unsupervised learning is not our interest in our today's lecture, so we will move to classification model directly. So within supervised learning, as I said, there are two different types, regression and classification. Regression basically deals with predicting an actual value or a real number, while classification deals with predicting a discrete or categorical value. So whenever a problem which machine predicts a categorical, a nominal, class, label value, it is called as classification problem. An example of classification problems are many, such as predicting whether tumor is malignant or benign, predicting whether result of game is going to get draw, win or loss. We can find out we can also use image classification, that is for a given image we can classify whether it is an object, whether it is an animal of a particular kind or whether it is a human. So that can be also done with the help of classification model. We can do disease prediction given a set of symptoms. What is the probability of disease of going to be that kind? And we can also find natural calamity predictions, such as I can find out the classification of whether it is an earthquake for a given set of images or for a given set of values. We can find out whether flood is going to happen there, or these kind of problems comes under natural calamity prediction. And the last one is handwriting recognition. Given a set of handwriting, we have to digitize the content or text which is given there. So whenever it is written by hand, whatever letter that we scan, whether it should be categorized as R or N or H, that has decision machine has to take it. That's why we need to train our machine. So handwrite prediction or handwrite recognition is an example of classification model. Let us look into classification learning steps. So there are 7 important steps in classification learning. As you know that for a problem we have to solve using a classification method. Then first thing is to do problem identification. Now within problem identification, we must have a well-formed problem which defines the goal of a problem. What will be an objective? What will be benefits that we will achieve from that solving a particular problem? So standard definition of a problem must be there in terms of machine learning, and what will be the long-term impact of solving a particular problem using machine learning has to be calculated in advance. If we are not going to achieve a required benefit, then it is no use to solve using a particular problem using machine learning of classification method. Second thing, we have to identify the required data which is used for training. So on the basis of problem identification, we must identify a data set which precisely represent an identified problem. So initially data set can be very wide, but we have to select carefully only that data which contributes in our classification prediction problem. So that data set needs to be evaluated and we have to identify the required data set. Before we can directly feed this identified data set into machine learning model, we must pre-process that data. Now, this third step of pre-processing basically deals with cleaning and transformation of data. We have seen different feature engineering process where we have seen how to deal with missing values and outliers, how to normalize data, how to convert required given data into required forms such as from categorical to nominal and nominal to categorical, from continuous to discontinuous value and discontinuous to continuous and vice versa. So all these techniques we must know because in order to identify what kind of data machine is going to get accepted. After making data pre-processing, fourth step is to definition of training data set. We all know that there is a set of input X to the system and corresponding output is achieved from a system which is nothing but variable Y. So from that particular data set, we have to identify what will be our training data set because after training a machine on what basis you are going to conduct test and how you are going to measure the performance of a model, that's why we need to separate out our training and testing data. So that has to be done. After finding training data set, we have to find out an algorithm which is suitable to solve a particular problem. Now remember, to solve a classification problem, we have numerous algorithms and each algorithm solves different types of problem differently. And so we have to here in this step choose a correct algorithm which solves our problem more correctly. So we have to either choose from naive based classifier, we have Bayesian belief network that we have already seen. Then we can also find out, we can also use k-nearest neighbor work, or we can use decision trees. We have support vector machines and numerous classification algorithms are there. We have to decide which algorithm is solving our problem more correctly. So that decision has to be taken. After selecting an algorithm, we have to train a selected model. So we run our training data on a selected model to tune the parameters of model. And once this model is trained, we have to evaluate its performance with respect to test data. Now, test data and validation data can be used to predict the label of already unknown data. So out of our complete data set, we are keeping some part, say approximate 20 to 30% of data is kept as test data and remaining is gone with training. So those data whose label is correctly predicted by classification model, which is previously known, is nothing but a good classifier or a good classification algorithm. So in order to evaluate, we have to find out, or we have to keep some reserved data which is called as test or validation data, on which we have to measure the performance of our algorithm. So let us quickly start with our second most classification algorithm. The first one that we have already covered is nothing but naive based algorithm. So second most classification algorithm is KNN, K nearest neighbor. It is very simple but extremely powerful classification algorithm. It has philosophy of that people which are having similar background or mindset tend to stay closer to each other. That is, neighbors in given locality may have some similar background. So it is working on the same philosophy. It makes a group of those data samples from training data which are having similar kind of information and makes a group of them and decides the label of that group according to training data. And whenever there is an unknown data which is unlabeled, whose label is to be found by machine learning classification model itself, which comes up for prediction, KNN algorithm judge on the basis of training data's label, and this that training data set elements which are similar is or nearer to unknown data is used to classify or to give the label of unknown data. So basically in one line KNN can be defined as to label unknown data element is assigned on the basis of class label of similar type of data which was present in training set. Let us see how KNN algorithm works. We are given one training data set. As you can see, this table is representing data set in which we have some set of attributes. These attributes are nothing but name, aptitude, communication, and this is our output attribute or classifier value, that is nothing but class. There are three categories of student. First one is speaker, second one is leader, and third one is intellect. Now this category or class of a student is decided upon some different input attributes. Now we all know the definition of nominal data. This nominal data doesn't contribute any information to decide or to predict the class value. So that's why even though it is present, this attribute is still present in dataset, but this consideration is not considered, this attribute is not considered for prediction. So in total we have only one and two attributes which will be used to predict the class of a particular student. And these attributes are nothing but aptitude value, and that aptitude score is given to a student out of 10. And this communication value or communication score of a student is again given out of 10. So this score will decide or define this class of a student. So here one thing can be observed that students which are having good communication skill as well as good level of aptitude. That means aptitude value as well as communication value both are very good score. Then we say that that type of student is of type leader. Student which is having good communication skill but not so good level of aptitude can be categorized as speaker category. And student is having not so good communication skills but a good level of aptitude is classified as intellect student. Now, here the question is what is this good communication and not so good level of communication? Or what is a good aptitude level or not so good level of aptitude. So that score we have to find out. Now that can be only found out using given training data. As you can see, this training data specifies what kind of students are having what type of data. Now, before we start or jump into the procedure, how this training data is used. So as I said, name is not contributing attribute. So name, even though it is there, not will use in order to predict the value of class. And out of this complete data set, our this green highlighted part is used as in training data, and this part will be used as our test data. Now, why we are using only part of data set as our test data? Because its label is known, but we will try to identify or predict this label based upon input value only. If that predicted label and this label matches, that means our classifier is working very well. Now, here before we start with KNN, we have to discuss two challenges which are faced by KNN algorithm. First challenge is that on what basis we are saying or deciding similarity of any two data elements. Say for example, if I say this particular data element and this data element belongs to same class or not. So on what basis, how we are finding that some of the data points are similar to each other and some of the data points are not similar to some particular data point. So we have to identify the basis of similarity. That is one of the challenge of KNN algorithm. And Second is nothing but out of these similar elements, how many similar elements of unknown data which are nearer or neighbor to it has to be considered to find out the final class label value. That means if one label or one data is not known and we have some set of neighbors around it. Okay, so these are the other data points and this is my question to data point. How many nearest neighbor that I have to consider out of these data points? Should I only consider one nearest neighbor or should I consider two different nearest neighbor? That is nothing but deciding value of k. How many nearest neighbor or k nearest neighbor has to be considered. So first challenge can be addressed using something called as measure of similarity. We have different measure of similarity such as Euclidean distance, we have Manhattan distance and we have Minkowski distance. By default, or I would say a common approach which is adopted by each KNN algorithm is to use Euclidean distance. And we know Euclidean distance is given as a square root of f11 minus f12 square plus f22 minus f22 square. Now, what do we mean by this f11, f12, f21 and f22? F1 is nothing but our feature 1 which is used or contributing something in prediction of a class. And feature 2 is nothing but communication in our case which is also contributing its information in order to predict a class. So F1 and F2 is now decided. Now if I want to find out the distance between first data point and second data point, that is the distance between Karuna and Bhuvan, then we have to find out the difference between first and second value of first feature. Likewise, I have to find out the difference between the second value of these second feature. That means I will find out difference between F11 and this is called as F12. Likewise, this is called as F21 and second value is called as F22. So basically we are finding its difference. Now some way this distance can be positive or negative based upon whichever the component is larger. Similarly here also if component is larger or lesser than first one then positive or negative value can be achieved. That's why we are taking square of these difference term. We are adding it and at the end we are taking square root because somewhere we have used square term. I'm keeping only this last data element as our test element. So I will not first consider whether it is Intel or not. I know, but I will try to predict the same label with the help of these two values. So we can represent this feature 1 and feature 2 in two-dimensional space where first attribute or first axis is feature 1 and second attribute is feature 2. Now, after plotting each and every data points, what is our question? We have this particular Josh record, which is having aptitude value 5 and communication value 4.5. That means it is being marked with this asterisk or star sign. Now we have to find who is nearest to this particular unlabeled data because class value, whether it is speaker, leader or intel, is not yet decided. That's why it is called as unlabeled. Now we have to find out the distance between some points. So we have came across our second challenge. How many nearest neighbor has to be found out? So we have decided that we will use Euclidean distance to find out the distance between any two different points. So our question data is this and other points distance, this distance will be calculated using Euclidean distance. This distance, this distance, this distance, this. Every distance that will be calculated using Euclidean distance. That is solved. But what about value of k? The value of k is nothing but user defined parameter which we have to given as an input to algorithm which decides how many number of neighbors will be considered for predicting unknown unlabeled data. So let us, in this case, let us see different values of k and how it affects the different output values. Now, distance from this George data, which is having value 5 over here and 4.5 here, we will find the distance between these two with and these two. And that distance is found using Euclidean distance, that square root of 2 minus 5 square plus 5 minus 4.5 square, and that value turns out to be 3.045. Likewise, I will find the distance between second value and George's aptitude value, second value of communication with George communication app value. So that distance turns out to be 3.354. Likewise, I will calculate distance of each data point from Josh. So this is the distance of each data point from Josh. So what in our particular graph, whatever asterisk was there, that star, we have found out the distance to each and every point. Now, have to consider all these distances to predict our final value? That means in order to decide this label, do I have to consider all values? No. Let us start with k is equal to 1. That means I have to find only the nearest one data point. So only one data point has to be considered. So out of all this distance, the smallest distance is 1.18. So V1.18 is nothing but Gauri. Now what is the label of Gauri? Label of Gauri is Intel. So in if k is equal to 1, we will say that label of George will be only Intel. Why? Because we have considered only one data point. If we have to consider k equal to 2, that means we have to consider two different nearest neighbor. So the nearest neighbor is 1.18. What is the second most nearest point? That is nothing but second largest value, which is 1.414. Okay, so we have Gauri and Sushant. One label is saying Intel, another one is saying leader. So if k is equal to 2, we are unable to decide because we have one vote in each. Maximum cannot be identified. One thing we can resolve using FCFS, but generally it is not preferred. Let me increase value of k. If k is increased and it is gone up to 3, that means we have to consider 3 different nearest neighbor. That means 3 minimum distance value. So minimum distance value is 1.118. The next nearest distance is 1.414 and the next nearest distance is 1.50. So here we have 1.414. So we have three different values, and for three different values, one is saying Intel, second one is saying Intel, and third one is saying leader. So the final output or final label, we can also say that it is an Intel type. Now initially we already knew that George with these value is of type Intel. That means in this case and this case, our algorithm has predicted target class correctly. That means this is an example of good classifier whether I will go with k is equal to 3. Later on you can experiment this data with the same value with k is equal to 4 and observe what is an answer you have received, and likewise you can go with keep on increasing value of k. The minimum value of k can be 1, that means minimum you will observe the one nearest neighbor, and maximum value of k you can use with all n data points, that is out of all training examples. There are n training examples and you are using all those training example is nothing but a largest value of k. That is the maximum that you can do. When k is equal to 3, only 3 nearest neighbors of test data are considered, and what is the majority is there, that will be decided. The final outcome of the result of data. Now this data deciding a value of k for any given arbitrary training set, what will be our value of k? So there are two different outcomes that we can keep the value of k very large. And extreme case, the largest value that we can keep of k is equal to the total number of records in training data. I cannot increase more than that. I can maximum find the distance to all other different data points. That is what max we can do. So the class label of, in that case, of majority of class which is given in training data set will be always assigned. In this case also, when I set k is equal to n, in that case also I have to find out what is the majority of classes that is saying, or majority of votes that are going with given test data will be the output. So they are assigning a label to test data regardless of class of nearest neighbor, because they are considering all other distant neighbors also. So in this case we are not only considering nearest but all neighbors. So this loses the beauty of nearest neighbor. Another value that we can keep, value of k, is very small. The smallest value that we can keep is 1. So in this case, what will happen if that nearest value or nearest data point might be a noise or outlier? So that noisy data or an outlier of training data set can also classify our nearest neighborhood, which might assign wrong output label to our test data or unknown data. So what should we do? What we value of k we have to decide. So the best value of k should not be very large or very small, but in between. One practice is followed that we can set value of k equal to the square root of number of training records. Say for example, there are n training records, I can keep my k is equal to square root of n. That is one of the best practice. Another approach that we can follow is to test several values of k. That means for each training or unknown data at different values of k, we can see that in which value of k we are getting good result or good performance or correct classification, and on variety of test data set, and at the end we can choose value of k which gives a good performance. So this is one of the good way, but it is as costly because for different values of k, we have to run different tests and measure the performance of each. And third approach we can go with is choose larger value of k, but always use weighted voting process. That means I can choose every nearest neighbor, that means all neighbors, but nearest neighbors are given more weightage. Their vote will be considered more important than any distant neighbor's vote. So in that case, we go with something called as weighted voting process, which is again which is considering more influential vote of neighbors, and we are having less influential vote of distant neighbors. So again, it is very good practice to go with this kind of options. So we have in total 3 different options that we can go with. We can choose value of k, which is square root of n. N is nothing but number of training samples. We can test value. We can test same algorithm for different values of k and choose the value of k which gives the best performance, or we can go with larger value of k and apply weighted voting process. Now look into nearest neighbor algorithm. We have to do for all test data point. That means in our case we have only kept one data point as our test point, but in reality there can be many data points for which we have to consider test and whose label is not known and we have to predict for evaluating its performance. For all these data points we have to calculate the distance, that is usually Euclidean distance of this test data point from the different training data points. So in training we have m data points, in test we have m data points. So for each data point I will calculate set of differences for all n training samples. For the second also we will have another training distance, and likewise we have m test data, we will have m test distances. We have to find the closest k training data point. So out of all these value, I have to find out k closest value. Say for example, this value is closest, this is closest, this is closest. In case k is equal to 3. In second example for test data, only 1, 2 and 3 value is closest. Here 1, 2 and 3 value is closest. So we are finding the k training data points which are closest to our test data, and if k is equal to 1, if we are looking into only one nearest neighbor, then we have to assign the class label of a training data point to the test data point. So whatever is matched in first place will be our output label. But if k is not is equal to 1, then there is a more larger value of k. We have to consider a class label which is predominant in our present training data point. So which is nothing but a majority voting, and assign that class label to our test data point. K nearest neighbors are called as lazy learners. Now, why they are called as lazy learner? As you know, lazy learners are those machine learning algorithms which do not follows a complete step of machine learning. Now, complete step is nothing but input data, abstraction, and generalization. So basically, no true learning is happen. Whenever the unknown data comes, it refers training data, and because on based of that training data value, it is predicting value. So actually, no learning is there. There is a no process that we have followed, which calls as generalized data, or we have abstractly presented that model data. It is never been that. So there is a no as such process of abstraction and generalization in KNN. That's why they are called as lazy learners. And it stores training data directly, applies their values on every unknown data that comes for an algorithm. But and let us discuss now what are the strength, weaknesses, and application. That is nothing but an SWA of KNN. S stands for strength, S stands for strength, we have weaknesses and an application. Strength is that it is very simple and easy to understand. As we have seen, the process is very simple and easy to understand. And in most of the system, recommended system, it is very effective. So it is always giving a good recommendation system design. And the time required for training a model is very fast. As you know, in reality, there is no as such training, only the training data is feeded. There is nothing is learned. So training phase is very fast, or I would say it will almost take no time. Only data feed time is there. Now, what are the weaknesses or cons? It actually, in reality, it doesn't learn anything. So it only predicts value based upon past value. So no learning is there in real sense. So since no model is trained, the classification process is very slow. Now, as you can see, what is slow and what is fast, that you must understand that training phase is very fast, but prediction or classification or prediction of unknown value is very slow, and a large amount of computational space is required because we are finding the distance of each and every point. That's why only after finding the distance to each and every point we will able to find out the nearest point. Okay, so every time it is always required to load a complete data and find the distance to each and every point, and later on find the nearest data point. It very nicely works with recommender system. We use recommenders. It has been basically used in Netflix and Amazon. They basically use KNN for recommending new products based upon past browsing history or purchase history. So linking is revealed from past purchase or browsing, which is widely used by popular e-commerce sites. Okay, and searching a document content. So within a document, if some one content is searched, we have to search same content on similar different kind of documents. So that is called as document content search, which is also known as concept search. Okay, so if similar concept is appearing in another document which is of another field that we have to search, then we can also go with KNN. So in today's lecture, we have seen different supervised learning algorithm under classification. We have seen the classification learning steps, and one algorithm that we have discussed is KNN. Thank you everyone for watching this video. This is Munira Topia signing out.